All right, so welcome to another video. This is one of the few videos I'll be posting just after I've taken CSE 230, just to make sure that everyone gets at least a good amount of information on both halves of the semester. So the original videos or videos I posted before this have been on chapters 4, 5, and a smidge of 6. The upcoming chapters will be what we learn in the first half of the semester. So more of it will be on MIPS coding, MIPS problems. I might do a little bit more of the quiz reviews, but I don't know due to time and other things I have as I'm making these just before the semester starts. So yeah, I'll quickly get into it and try not to spend too much time on the what is it? I won't spend too much time on focusing on the other stuff, and will be two long videos. Hopefully I'll try to get this stuff rolling. So screen share if I need to. So on the right side of my screen, I have what my notes were, the left are what were in the slides. So I'll try to go through each quickly. So first thing we talked about in chapter 1 would be performance. So we have response time, which is start to the end of a task. There's the throughput, total number of tasks done in a given time. A better processor would have better response time, more processing, better processor equals an improved response time, and more processors you have a higher throughput, so more tasks that can be done. With elapsed time, the total number of time to complete the task, CPU time, computation time, which is the execute instructions times is blank times, sorry, just the execution of the instructions, which is CPU time. Excuse my poorly drawn notes. I'll try to translate them for you as best I can. So we go over that. Response time, elapsed time, how to figure out the performance. So pretty much you would take whatever the execution time is, performance is 1 over execution time. It goes over quickly, just how to figure out which time is better. We have CPU time, which is clocks or CPU clock cycles for a program, times the clock cycles. Another way that can be done is with clock rate, where you would have the CPU clock cycles for a program and you would divide that by the clock rate. So the first example that was on here was compute that clock cycle, compute the clock cycle of 4 gigahertz per second, or the cycle time. So you would have 1 over 4 times 10 to the power of 9. Multiply that by 10 to the power of 12 and get 2.5 picoseconds. We do the 10.25 just to make sure that you get this amount of seconds, 250. But if you were just to divide it, you would have, I think, you would just have 0.0000 and then at some point 25 seconds, which would be picoseconds. Then a little bit more about performance. If we want to improve it, we would decrease the number of required cycles, decrease the cycle time, or increase the cycle rate. For the sake of this video and the future videos I'm about to put out, I'm not going to go too much in depth into the example, so I'll just hover over it, and if you'd like, you can go over it and try it yourself. So we have this example, we have the next example. Number of instructions, mainly cycle time. Chapter 1 is mostly on introductions and how to do these calculations. Clock cycle. Yeah, pretty much very minimal knowledge for chapter 1. Not too much is going on other than a basic introduction. So what I'll do is I'll just quickly go over chapter 2 as well in this. So that way it'll be a lot quicker, and hopefully I'll try to do some chapters along with that. And overall, maybe I might just be able to put all of them in one video, since chapter 2 and 3 both have to do with MIPS. So we're going to chapter 2. So this is where we learn about hexadecimal, binary, decimal. We learn all of these conversions. This should be knowledge you should know. But just in case, you have your decimal numbers. So 8 would be 8 to 10 to the power of 0, 0 to 10 to the power of 1, 1 to the power of 10. 2 to calculate the first decimal place, which would be 0, 0 times 2 to the power of 0, 1 times 2 to the power of 0, and then for 16, and then for hex, you have your C divided by 16 to the power of 0. You know, the base would always be whatever multiple or whatever the range of values can be in one digit place. So since it's hex 16, so 0 through F, 2, 1, 0, and then 10 is 1, 0 through 9. Just go for a quick go. If you guys want to refresh yourself, I would just quickly find a video somewhere on these conversions. You'll have to know them more. And then we finally start going into MIPS arithmetic and MIPS code. Another thing that's very important to have would be not the registers, but let's see if I can find it. This. So the MIPS green sheet. I know during my semester she said it a lot and we used to make fun of it a lot, but for this one you will definitely, trust me, you will definitely be using this a lot. It has the opcode on how to write machine code for this. It has all the different or the correct placement. So you have R type, I type, J type, and then every single instruction that can be used. Along with that, even a set of pseudo instructions, and then all the register names and their numbers, which is something I made sure to put here. You have your return address, frame pointer, stack pointer, global pointer, the temporaries, save registers, argument values, 0. Let's go back here. So when going over MIPS, there's different amount of arguments that you could have or inputs you can have. However, usually at most there's 3 inputs. So you would have your destination register, which is what I have first, the first input and second input for the register. It's never something you can't just do. So let's say if you have something like this, you can't do add register at A or to A, you have to do B. If you have the destination of A, input register B, C, and then D, this is not possible. What you would have to do is you have to do 2 lines of code where you would have the right destination, A, B, C. You have destination at A, you add register B and C together, which that value will be in A. To get this value here, you want to put this in still in A, but you'll add whatever value is in A, and then add D, since A, whatever is in A now is B and C, the value of B plus C, you add that to D, then you get A, so that'll always be there. Registers, 32 bits, which are 32 bits long. This is crucial information to know, not at the beginning, but when you get into doubles. If you get into floats and you have a double float, since those are 64 bits, I'll talk a little bit more later. That's like one of the crucial things to know, because you can store more stuff and there will be more binary things to note in there. So there's spilling registers. What if a program has more variables than registers? most frequently used variables and registers, other variables in memory, access variables in the memory, loads and stores. So pretty much spelling registers, it shows how what is saved, what values are saved or not. Some good knowledge to know, but I don't think you'll really need to know too much about it. Again, there's more examples, a summary of the lesson. And that's pretty much what goes on throughout majority of chapter 2. During this time, which is here, most of it is just going through, at least the first half of the semester, you go through machine learning, or not machine learning, sorry, MIPS. So the next couple, you'll go on to loops, procedure calls, and other ways to implement these values and other instructions. So continuing on to this, pretty much another basics. They're adding on to the basics. We have machine language, which is pretty much binary. So there's the opcode. I'll actually move my green sheet over here. You have the opcode, the first register input, second register input, and then register destination input. So wherever the value is, there's a shift amount, which depends on the instruction. Usually if it's, I'll try and zoom in some of these, but if there's shift left logically, since it's R, you have to put this, whatever value is here would be the shift amount, or you're dividing 2 to the power of this value. And then there's the function. So on the MIPS green sheet, there's the opcode / function. So this beginning will be the opcode. And then the last one will be the function value. But this is only for R type. As you see, there are some that don't even have the /, and that's because that's the opcode. I type, J type instructions do not have the function value. So what you would do is, as you see, there's just one value, that would just be the opcode. Here's just a quick example. If you'd like, you can pause. There's another example. I'll just go through and give you a few seconds. If you want to pause it, you can. Most of the time, you would just be taking values here. You would take values from this part. I didn't go too much into these, but it's pretty simple what you do. So here it says $8. So what would $8 be? If we look onto the right side, that would be T0. You're pretty much matching whatever the number correlates to the register. You put that as the value. So add here, register T0, you would have 0, 1, 0, 0, 0 to get 8. And the same would go for the other registers, and same for shift amount. For I type instructions, it's very similar. Pretty much you have your opcode, the 2 input registers, or pretty much it would be the input or source. It says source register, but pretty much whatever you need to add. So on this one, if you're adding, so if you're storing, or let's just do add immediate. So if we're doing add immediate, it would be add $1, $2, 4. So pretty much 1 would be here and 2 would be here. You'll also learn about load word and store word, which accesses memory. But either way, you'll have a load word, 1, 0, 2. So 2 would be the RS, 1 would be the destinations, and whatever you're loading here from this value would go here, and then this value right here would be the immediate, and right here would be the immediate. So 4 is pretty much whatever constant value is in the instruction. And in case if you're confused and you don't know, well, what is this instruction? Is it an R, is it an I? There is a format right here. It'll say R, I, or J. And just a quick tip, usually branch instruction is also an I. So I'll do a quick example on how to figure out what that would be or what the immediate would be for I. So start with this line, this line, this line, this line, this line. So you have each line of code here. So pretty much, let's say this is the branch if not equal to. So and let's say if it branches, it goes to here. Pretty much you'll start from this line and then count the number of lines it takes to get here. So 1, 2, 3. Or similarly, the lines in between the branch and the exit or label that you're going to. And then along with that, later on, we'll learn about the jump, which I'll try to skip to real quick. Actually, I'll go over like some of these. I'll just hover over the machine code for examples and the answers. And if you want to, you can look through it and try to compare it. And then we go over the J type, which is the jump. So pretty much if there's a J, you're just jumping to whatever section of code the label is at, which usually the label will have label and then colons. So as like here, label colon, and then the instruction. And that's usually how we do loops. You'll use a branch instruction, and then you use the J instruction to go back to the top or whatever label would be. So memory operators, load word, store word. Real quick, you'll have half word and unsigned. So a quick thing to know, a word is 4 bytes. Each byte has 8 bits. So that means there's 32 bits in a word. A half word would have 16 bits, and load LB, which is load bytes, would be just 8 bits. So depending on what you need to find, which during the course it may change. I won't go too much into depth. I just want to try and help out with the basics. That way things can be understood a little bit easier and you say, hey, I can see this. I don't have to be left behind trying to figure out what I need to learn here, but just keep that in mind whenever you need to find a byte. If you've taken 240, you can compare this to the type of information we need. So if we need to learn bytes, or if we need a load byte, depending on the amount of bits or bytes we need, you can compare that to like integer, char, and the various data types. Which is said a little bit here. So loops, we have C, there's a while statement. So in order to increment it, you have your loop. And then once you reach the end of this, you'll keep going all the way back up here until you meet this requirement, and then that's the only way you exit. Another real quick thing about multiplying and dividing. So first, you'll do let me just find it. Okay, right here. So there's multiply, and then there is divide. Usually once you do that, as you can see, there's only RSRT. There is no, what would you call it? There is no resulting variable. It's just you put in your two input values. What you would do in that situation, you would use, let me just find it. You would use the move from low and move high variables. I think I might have skipped. I might have quickly skipped that. I'll try to go back and find it real quick. Okay, yeah. So in 3, multiplying and dividing. So multiplication, MF low, you get the lower 32 bits in the multiplicand result register, which pretty much is a register that holds the value of the results of multiplication and division. So the low 32 bits will be stored in MF low, and then the higher 32 bits will be stored in MF high. For division, MF low will be the quotient or the result from the division operation, and then MF high is where you would get your remainder. So you don't have to do any fancy calculation or code. You just have to do MF high. So we learn more about the other J-type instructions. On my right, there's jump and link, which is similar. You would just have JL and then a label, and then it would go to wherever that label is in the code. But usually when you do JL, it would be going to a function. So if you had a main method here, you would use JAL, and along with that, that's when you would use the argument registers to complete the values, because the temporary values don't stay during these. The temporary registers make clear. So what you do before that, or before you JL, is you save them to memory, or you would save them to the stack pointer, like in 240. Stack pointer is used for, you would use it to allocate it as you keep going through the code, and then you give it back once you're finished with it, like dynamic memory. And then whatever values you need for arguments, you would put that in there, and then you can use the T values or the T registers or any other registers for calculations. And then along with that, you would use the V0, V1 registers for the values, or to return the values of the whatever function you're doing. And then at the end of any function, you would have JRRA. It is an R type, but it is an R type, but there's not too much you need to do. If it doesn't include any of these parameters, you would just keep it at 0. So just an example, if you have add, there's no shift value. So pretty much every 5 bits would be just 0, 0, 0, 0, 0. And for the J type, there's machine code, but you have the opcode here, but what would be, you're probably thinking, what would be the machine code for the address? So let me just go through, try and find it. Down here is more of a specific example of what would be done. So you have your load words and store words and the stack pointer. Then again, one thing is the stack pointer. Make sure you give the data back and close it up. So you say, okay, I'm going to use 12 bits or 12 bytes. Yeah, 12 bytes, and you give those 12 bytes back. And here's another example of using JA or JAL as a function. And along with that, you can do recursion in MIPS as well. It's very tedious. If there's one thing that you guys should know is that it's very tedious. MIPS is a lot more tedious than, or will be the most tedious language you use in any other course. From what I've seen from people writing code in Python, MIPS, it's gonna be a pain, but you still have to do it, know it, and try to nail down all the small stuff so that way you can hit the ground running whenever you need to make a code. So then quickly for factorial, you have your add-I, you take whatever you need, you go through it, you have your, make sure you have your base case up here, and then go to the, keep doing that base case, and then whenever you're done with that, you do JL factorial. So that way you go back here, you save more of that instance, and pretty much what you're doing is you have, you know, your first stack pointer. I'll just do SP1. You do whatever you need to. SP2, you're constantly adding to the stack pointer and other stuff you need. So hello. Sorry, I just want to make sure I was using the right microphone. I'm just going to quickly go through this and get through this last point, and then that'll be it for this video. So I'm just going to clear this annotation out. So yeah, that's pretty much the entire what you're doing for, or the best way to describe this code. You save whatever value you need, check your base case. If the base case is good, if not, you go through here, and pretty much once you're done, so let's say we go through here, I go all the way down, I say JRRA dollar. Pretty much once you do that, you return all the way back here, you go to the next line, it goes all the way down, JR goes all the way down. Pretty much JAL jump in link, it saves the, or sorry, with here you have $RA. You're saving whatever the return address is. You're loading the word to RA, so that way it remembers, okay, I need to go back here. I need to go to this instance with these specific values. So loading and storing RA helps the program remember, okay, this is which stack pointer I'm on, or this is which part of the code I'm on. And then the last section I want to talk about that I got cut off because I was focusing on the factorials. It's not this. I'm just skimming through because, all right, here it is. It's pretty much the last part. So this is going more into branch. Here it is. So for this one, we have our machine language. For jump, you see there's two. We have J loop and then 2000. So how do we get the 2000? Well, the loop is, while it's covered, it's all the way up here. It's in the first line. So pretty much what you do is you take whatever the PC counter is at that point and you divide it by 4. So since it's 80,000 here, you divide by 4, you get 20,000. Convert that to decimal, and that's the last 26 bits of the address.
for examples here. Chapter 3 goes into 2's complements. I'll make a separate video on that later, but right now that'll be it. I just want to quickly go through the basics of MIPS. So thank you for watching. I'll try to make a chapter 3 video on soon, and I will hopefully see you guys. Hopefully, I hope that you guys aren't doing, this isn't scaring you too much, but just make sure to practice and you should be fine for this for whatever semester, whatever you're taking the class. Thank you so much for watching.